Hello, today we will introduce you our project, which is a distance and tilt measurer built using Arduino. This device is designed to accurately measure the distance to an object and its angular tilt using laser ranging and accelerometer sensors. It's a compact, low-cost solution that can be applied in robotics, automation, and structural monitoring. So next is our project concept. This project is conceived and engineered to aid in measuring distance and measuring the angle of its tilt, and to demonstrate sensor fusion by combining data from multiple sensors. It may be intended to be utilized by, for example, rearranging furniture, or even give robots a sense of balance and control with orientation awareness and detect obstacles. So how it works? This is designed while always keeping simplicity and readability in mind. So we are made sure to make measuring with this understandable. The circle on the bottom right with a visible rotating line inside corresponds to the tilt of the device, and the circle will be filled to indicate that the user is holding it parallel to the ground. And next one is our component. So first is Arduino board that use Atmega T2X microcontroller. Second is OLED display. Third is time of flight VL53 LOX sensor. We use this one for calculating distance. So for the VL56 LOX, VL53 LOX is a time of flight laser ranging sensor. It measures the distance to an object by emitting an infrared laser beam and calculating the time it takes for the light to bounce back. It is compact, accurate, and widely used in robotics, drone, and object detection applications. And next one is MPU 6050 accelerometer and gyroscope sensor. We use this one for calculating tilt angle. So for the MPU 6050 is a 6-axis motion tracking device. It combines a 3-axis gyroscope and a 3-axis accelerometer on a single chip, and is widely used in applications like gesture detection, tilt sensing, motion tracking in drones, robotics, and gaming device. And next one is breadboard and jumper wires. So next is wiring. So each module are I2C device which all have 4 pins in common. So first is VCC or power. We connect with this one to 5 volt or 3.3 volt pins. Next one is GND or ground. We connect this one to the GND pins. Third is SDA or serial data. We connect this one to A4 pin, and last one is SCL or serial clock. We connect this one to A5 pin. So this module are all connect to the same pin in parallel, and Arduino can differentiate them by having different addresses.
Now we're going to talk about how the code works. In these first 6 lines here are for importing libraries. The first one is just for I2C devices. Then these next 2 are for the OLED display. This next one here is for the VL53L0X TOF sensor. The next one is for the accelerometer with this name. And the next one is for importing functions that are related to mathematics, like trigonometry or the pi constant that we use for the circle. The next one is to define the OLED display. The first one we define as the width of the screen as 128 pixels by 64 pixels, and the address of the OLED is 3C. This one is set to -1 because our display doesn't have a reset pin, and this one is for initializing the Adafruit SSD1306, which is for the display. Next one is for setting up the TOF sensor, and the next one is for the accelerometer. These variables, the first one here The first three are raw data that's extracted from the accelerometer, and the next one is when we transform them into usable variables. The next one, we define the circle radius to be 20 pixels, and the offset is just to move the circle just 5 pixels from the corner of the screen. And this is the value of the Earth's gravity in meters per second squared. This one we defined as the line color of the diameter in the circle. So now we are setting up each I2C devices. This one waits for the serial port, so when it becomes true we can continue. So while this begins the I2C communication, and this one initializes the OLED. So if this is false, then that means that the circuit is not connected properly to the display, which means it's failed. So we halt the code here. And if it's true, then we can continue here. So the OLED is okay. So then we initialize the sensors. So now we initialize the time of flight sensor or TOF sensor. So if it's false, that means it's failed. It's not connected properly. But if it is, it's okay. And then we continue. And then so on with the MPU 6050. So if it fails, it says it fails. If it doesn't, it'll continue. These are just the general initialization functions for the accelerometer, which I won't go into detail much. And then when it completes, it clears the display, which has been printing stuff like setting up the sensors like before. Now we go into the part where it displays the values of the sensors and recording them. This is just for debugging the code, which I'll be explain lastly. This one is a variable for distance that's recorded by the TOF sensor, and distance valid is like to make sure if the value of distance is valid or not. So if it's equal to 65,535, which is like the limit of the sensor, and I have decided that the sensor should probably only detect till 2000 millimeters, because maybe it's 2000 millimeters is like 2 meters, so we set it that as the limit. So if these are true, then distance valid is false, so it's invalid. And now we get the acceleration parameters as raw data, and then we convert them to usable data by dividing them with this value and this value, which I won't go into detail about. Now we'll define the tilt angles that we are actually going to display on the OLED display. So tilt angle rad, which is the tilt angle in radians, will be calculated as the arctan of the acceleration in the y-axis and the x-axis plus m pi. I added m pi because while I was calibrating it, I was putting it upside down, so I have to flip it by adding pi. And now we are converting the radians into degrees by multiplying 180 over pi. Now we get to start displaying these values. So firstly, it clears the display because each iteration must be cleared in order for the next iteration to be clear. So we set the text size to 2 and set the text color to white. We set the cursor at 0, 0, and then print distance. And so if it's valid, which we looked at here, then we can continue printing. Distance divided by 10. We divided by 10 because we wanted it to be in units of centimeter. Or so if it's not valid, then we will just print more than 200 centimeters. Next, we will set the cursor at 35, set the text size to 1, and we will print the tilt and the tilt angle. And this prints the symbol of a degree symbol, which is like a tiny circle on the top. And then we initialize two more variables, cx and cy. Cx is the display width minus the circle radius minus the offset, and cy with the display height minus radius minus the offset. This is the center of the circle that we are going to use to print the circle. So now, this is the conditional that's used to show if the user is holding the device parallel to the ground or not. So if the user is holding around less than 4 degrees, it will fill the circle with white and print the line in black and show that it's parallel to the ground with 0 degrees. Or else it will show as normal, draw a circle, and the line will be white. And this, I made another variable called line len, which is just a circle radius but -4 to make it just a bit shorter than the diameter. So x1 is the cosine. Actually, in all of this I have actually made it, making a prototype of it in Mathematica. So this is the resolution of this OLED screen. I printed the circle and I tried to make sure if it works in this first. So it really works as I intended, but then we decided to move the circle to the bottom right corner because it needs to print some information about distance and angle, so we moved it to the bottom right corner. And then, well, after these, we display the line, and then we display the entire thing. This function needs to be declared in order to print everything that was told before it. And then this next part is just for debugging. This is like what we said we were going to talk about last time, which is this on the line 108, which is used to just measure how long it took the code to run in these entire lines. And then we delay it by 50, so the measurements will be reset every 50 milliseconds. Now it's time to demonstrate how it works. Firstly, when I plug in the Arduino, there will be a startup screen to make sure that all the sensors work. And now I am demonstrating how the distance sensor works. And now I'm showing how the accelerometer works. As you can see, when I tilt at an angle below 4 degrees, the circle turns white to indicate that the device is parallel to the ground.